We've got a smoke plume carrying a uniform concentration of 50 micrograms per meter cubed carcinogenic particles, and it's traveling to a nearby skyscraper with an open window of cross-sectional area A and a thickness delta X equals 0.2 meters. The wind is moving with a uniform speed of 3 meters per second. The diffusivity for smoke particles in air is about 10 to the minus 4 meters squared per second, and the horizontal turbulent dispersion coefficient is 0.5 meters squared per second. Assuming no smoke particles are on the other side of the window, calculate the net flux of smoke particles at the skyscraper window from advection, molecular diffusion, and turbulent dispersion. Okay, so let's draw just a quick little picture. So I've got some sort of smoke plume coming in. Here's my building. Okay, and then I've got some open window here with cross-sectional area A. And it's going to have its own little thickness into the building, which is given by delta X. Now there's going to be people inside. Well, I guess there doesn't have to be, but if there were people inside, what would be happening is they would start seeing these smoke particles enter the room, and assuming that it's a closed room, the smoke particles won't have anywhere else to go. So these fluxes in general will be changing over time. So we're just going to look right at the instantaneous moment the smoke particle or the smoke plume reaches the window. Okay, so let's start with advection or advective flux, because why not? So to do this, we just need to find all our expressions for each of these different fluxes. So our advective flux in one dimension is just our concentration times our velocity. So all we have to do to find the advective flux is multiply these two quantities, which is fairly easy to do in one dimension. So this is equal to 50 micrograms per meter cubed times our velocity, which is the wind speed of 3 meters per second. So times 3, oops, that doesn't need to be tiny, times 3 meters per second. This meter will cancel out with this, so we'll just get meters squared, and this will give us a concentration of, an effective flux of 150 micrograms per meter cubed. Okay, so we're done with that one. Now for diffusive flux, we have minus d dc dx. Okay, now if we were to actually calculate an integral, we would need to know some sort of function for c, which, sometimes we do. But in general, we don't really know this function, so what we do is we just approximate it. So this is approximately equal to minus d times the change in c over the change in x. All right, so we turn infinitesimally small derivative to a finite small change in c over change in x. Okay, and this is going to be exactly equal to our diffusivity. So diffusivity for smoke particles in air is 10 to the minus 4 meters squared per second. So minus 10 to the minus 4 meters squared per second. And now we need to make sure we get the direction of the concentration gradient correct. Okay, so we're going from outside to inside the window. So that means our C final is the concentration inside the window, and our C initial is our concentration outside the window, and delta X is just delta X. Okay, now this is equal to meters squared per second. C in, assuming we don't have any smoke particles on the other side of the window, then this is just 0 micrograms per meter cubed. Our outside concentration is 50 micrograms per meter cubed, and delta X is 0.2 meters. Okay, and plugging all these in, you should get JD is equal to 0.025 micrograms per meter cubed. All right, so let's write these over here so I can have space for the turbulent dispersive flux. So 150 micrograms per meter cubed, JD equals 0.025 micrograms per meter cubed. And one thing I want to note here is that both of these positive fluxes indicate the flux is going into the window. So I'll just make a note here, positive flux indicates into window. Okay. All right, let's make some room for our turbulent flux. So we have something that looks remarkably similar to a diffusive flux, except instead of our diffusivity, we have our turbulent dispersion coefficient, dc dx. We do the exact same thing and we approximate this as finite change in concentration over a finite delta x, and this is exactly equal to 0.5 meters squared per second. C in minus C out is the same thing, 0 micrograms per meter cubed minus 50 micrograms per meter cubed, all over 0.2 meters. I forgot to check the units earlier, but we'll have 1 over meters to the fourth power, because we have meters cubed and meter. But we have a meter squared on top, so we'll have this. I want this. So this meter squared will cancel with meters to the fourth, and we'll just have meters squared down here, and we'll just have micrograms on top and another second on bottom. And if we plug all these in, we get a turbulent flux of 125 micrograms per meter second squared. Oh my gosh, you guys, you didn't correct me. These units are all meters squared per second in the denominator. Meters squared second. Okay. All right, so before you turn the video off, let's talk about some findings. Okay, first of all, diffusive flux is way smaller than advective and turbulent flux. This is generally going to be the case as long as you have advection and turbulence. If you have both those flows, then they're always going to be larger than the diffusive flux. I mean, the diffusivity is 10 to the minus 4, but the turbulent dispersion coefficient is 10 to the minus 1. Okay, so several orders of magnitude larger. And then our velocity is 10 to the 1, right? Or 10 to the 0, I suppose. Okay, now the other thing is that as long as the wind stays constant, the advective flux is going to stay constant. Okay, so this won't change. However, as concentration starts to pool up inside the window, this term C inside, is going to change, right? So if you can imagine, if you got a closed room inside, you're going to be pumping in a bunch of smoke particles into the room. Those particles have nowhere else to go, and so at some point, the smoke particle concentration inside the room will be larger than the smoke particle concentration outside the room. Okay, so that's kind of the major work of air quality research today, is looking at the difference between inside or indoor and outdoor air quality, because indoor air quality tends to be much worse than outdoor air quality because there's nowhere for these smoke particles to go. Okay, now what would happen if this suddenly became 150 micrograms per meter cubed, for example, minus 50 micrograms per meter cubed? We still have this negative sign, which I dropped, but we still have this negative sign here. So let's just write this out. Imagine C inside equals 150 micrograms per meter cubed. Therefore, JT would be minus epsilon T times 150 minus 50 over delta X. So this would be a net negative value, right? So that would indicate now our turbulent flux is actually sending particles from inside to outside. Okay, so if we have a negative flux, that's particles going out of window. Okay, and then we would get the same thing for a diffusive flux because we have the same concentration gradient term. So we'd still be pumping particles in through advection, but as soon as the concentration inside the building got high enough, all of a sudden our turbulent and diffusive fluxes would switch direction.